Alright, this section is going to be introducing kind of really just one new topic, and we're going to go deeper into integrating as well. But the new topic is slope fields. So slope fields and differential equations, there are 10 problems in this packet. They are all AP questions from the past. You can look up the scoring online. If you just literally look up, consider the differential equation, blah, 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 and it'll pull up the exact AP question that it's related to. So I'll show you that in just a minute too, how they grade all of these things. Because I know some of you guys have been asking what points are given for what. We need to see the work that leads to the answer as well as any justification. So really that's the majority of what we need to see. I know that's a very vague answer, but that's really all we need in order to give you the points that you deserve. So let's just get after this. A slope field, essentially what it is, you've been seeing it all along. The last question here is a slope field. So this is a slope field for this function, for dy dx equals 3 minus y cosine x. So essentially, right, dy dx, that is the slope of my original function. So all this is saying here is if I follow the slope, let's say it has to go through this point, and if I follow the slope, my function would look something maybe like that, right? So it's kind of following the slope of the original function, right? So the slope at each given point. So to find all of these points, you can literally throw in x and y into your function up there and figure out what the slope would be at that given x and y value. That's all that slope fields are, is they're essentially graphs of the slope for each point x, y, all around. If they ask you to do it on a free response portion, it doesn't happen very often, but these are some instances where it does happen, where they ask you to actually graph the slope for each thing. So on the axes provided, sketch a slope field for the given differential equation at 12 points indicated. They have 6 up here, 6 down here, so that is 12 points altogether. For -1 to 1 for x, and then sketch the solution curve that passes through 0, -1. And notice here, y cannot be 0, right? So y cannot be 0, and it's going from -1 to 1. So in order to graph the slope fields, I'm just going to plug in values, right? So if I take dy dx at, let's do that point right there. So that would be at 0, 1. Well, that would mean that x is 0, y is 1, so my slope there is 1. So what I would do is at that point, I would graph a function with a, or not a function, right? Just a little line, a little tick that has a slope of 1. So I'm imagining in my line, or in my mind, that it has a slope going like that. So it's a little bit off, but it's pretty close. And they're not going to like get a ruler out and see if you went exactly through it. They're not going to be that picky about this stuff. But that would be how you do the first one, right? So if I do the same idea, but I use a different point, let's say I use 1, 1. Right, then that would mean the slope is 2 here. So at the point 1, 1, my slope is 2. So I'm imagining in my mind that I'm going through that point to get that slope of 2. Yeah, so it's really just going around and doing all those points. So if I have -1, 1, then I would have 0, and really any time x is -1, it will have a 0 slope no matter what the y value is, because -1 plus 1 is 0. So let's see, when x is 1, if y is 2, so I'm thinking about this point right here. If y is 2 and x is 0, then I have a slope of 1/2. So I'd have something like that. If y is -1, then I have a slope of -1. Just going straight down here. If y is -2, then I have a slope of -1/2. So I have something like that. And let's see, if x is 1 and y is 2, that's 2 over 2 would be a slope of 1. If x is 1 and y is negative 1, that is negative 2. And this would be negative 1. So that would be your graph there. And then the other part of this question, sketch the solution curve that passes through 0, negative 1. So I'm just going to follow the slope all along these values where the x and y are the same. That's a straight line until I get to this point where it is 0. And I can't be there. Notice it's an open circle. I think they do check for that in their answer. I can't remember. But that's an open circle because I cannot be equal to 0 for y because it is divided by 0. Okay, and that's all that you're really going to do. That's the most that you are ever going to do on those slope field graphs. Is do the slope at each point, and then maybe they'll ask you to sketch a solution to a certain thing. Okay. So while the slope field in A is only drawn at 12 points, it is defined over every point in the xy plane for which y does not equal 0. So notice they even say y does not equal 0 there. Describe all points for which the derivative is equal to negative 1. So for part B here, I'm trying to find where the derivative is equal to negative 1. So I'm going to take my derivative of x plus 1 over y and set it equal to negative 1. So that would mean that negative y equals x plus 1 if I divide it up, or multiply it up, so that y is negative x minus 1. So that would be all of the points when x and y have this relationship where the derivative is negative 1. That's it. That's all the points. So you don't have to state anything crazy. That's it. That's all we're looking for right there. Okay, find a particular solution. V equals f of x. Well, I think that was a y. I think it got erased. Yeah, that was a y. Y equals f of x to the given differential equation with initial condition that f of 0 is negative 2. So essentially they're saying it's going through 0, negative 2. So it's kind of going through this point down here. It's not what we graphed, but it doesn't really matter that much. So let's see. Let's take our derivative. dy over dx is x plus 1 over y. All right, so now if I need to take the antiderivative of this thing, this is where I like to start talking about the separation of variables early when we started doing derivatives, because what I would like to do is get the y's on the same side, and I would like to get all of the x's on the same side, and then I can integrate both sides. So what I'm going to do is multiply the y to both sides, so that'll be y dy over there, and then multiply the dx to the other side. So this will be x plus 1 dx. So what I come out with is y dy equals x plus 1 dx, so that now I can actually take the integral of both sides. So if I take the integral of both sides to get rid of those dy's and dx, let's see, the integral of y would be y squared over 2. And I would have a plus c with this, right? And then this would be x squared over 2 plus x plus some other c. These are two different c values, could be two different c values, could be the same, I don't know. But we can combine them together on the same side, and I'm going to go ahead and multiply by 2 so that I get y squared equals x squared plus 2x plus some constant. All right, so I moved over the c, I subtracted that over, so I combined them into another constant. I don't know what the constant is, but it's some other number. I also multiplied by 2, right, this 2 right here, to both sides all together. And still, if I multiply that constant, it's just going to make it a bigger constant. So I still don't know what that constant is. Doesn't really matter that much right now, but we can find it. All right, then the last thing that I would do is actually find that value. Well, not last thing, I'm sorry. But the next thing I would do would be to find that value of c. So since it has to go through negative 2, 0, or 0, negative 2, I can put in negative 2 for the y and 0 for my x's. So c would come out as 4. So I come up with the equation y squared equals x squared plus 2x plus 4. However, that is not y. So in order to get y, you can take the square root of both sides, which in taking the square root, I would have a plus or minus x squared plus 2x plus 4. But here's the thing, is that plus or minus, that would have a line going up and a line going down, right? If I do plus or minus, I have something going here, I don't know what it does, and I have something going there. But we want the bottom part of this function. We don't want to take that positive part of the function. So what I need to do is get rid of the positive part of the function so that it goes through that point in 0, -2 only. And I do believe they say, well, they don't, but usually sometimes they'll say it's a function. But all I need to do is say that my particular solution is just the negative part of this graph. Okay, so that would be my answer. That would be my answer there. And I would have the differential equations up there. And Notability froze on me. That's wonderful. Okay, let's try again. Okay, cool. All right, so if I pull up the solution to this problem, let's see what they give us, right? So there was the same thing we had with the open point through there, right? So they give 0 slopes, they give a point for that, they give non-zero slopes, they give a point for that. So all of these over here were worth 1 point, and then all of these other slopes were worth 1 point. And then you have the solution curve going through 0, -1 was also worth 1 point. So that first part was worth 3 points, which is pretty big to me in just a graph. Okay, and this part B, really, description is what they give a point for. That's all they're looking for. This is the perfect answer, so to speak, but this is all they're really looking for in this. Okay, so now they give a point for the separation of variables. So there's 1 point right here, just that step. They give 1 point for the antiderivatives. There's 1 point right there. They give 1 point for the constant of integration, which C would be 2. What did I do? Oh, they had it work differently. They left the 2 divided out. Right, so they would give us a point for that C because our C is 4. Uses the initial condition, right? So it's going through 0, -2. You kind of have to use that to get the value of C, so those kind of go hand in hand. But using that initial condition is stating this function right here. So even if you didn't do the square root, you would have gotten a point for that. Then finally solving for y, you get a point for using that negative. So check it out. If you do not show the separation of variables, they will give you 0 points. So you have to show that separation of variables. I've actually been somewhat lenient in some of the grading that we've done so far, in that you can't justify wrong answers. That's not possible. So you haven't been getting a whole ton of credit for that, but every now and then I'll be generous. And I can't remember what I was about to say. Right, there has to be good start to the problem. They have to see that you understand the calculus and how you're getting to what you get to. So that's why I really preach to you guys. You got to show your work. Really, everything that I'm showing in the notes, you need to be showing in your quizzes and your tests. Max 2 out of 5 if no constant of integration. So if you don't solve for this C, you're only getting 2 points. No matter if you have this answer later on, well, I wouldn't think you would get that. So I'm not sure what they mean by that. But even if you look these things up too, you can kind of see what other students did on this test. And if you scroll all the way down, you will see how they graded it as well, if you're curious about what kids got points for and what they didn't. So that's always kind of interesting to see to me too. Kind of helps me in grading these things. Also, I talked to Mr. Osborne, so he's been grading these for years and years and years. Okay, so moving on. I'm going to do the first 3 with you guys. And then the rest of these 7 will be for your homework. Should be plenty to get you guys good at practice on this stuff. All right, so this next one, right? Again, you are going to graph the slopes for all of these things. So take a minute, pause the video, see what slopes you come up with, see how they come out for you, and then check out my solution. I'm going to pause the video too, and I'm just going to go ahead and show the solution. All I'm doing, again, you have to plug in the 0.11 to your derivative and see what the slope is, and then you're just graphing the slope. If you guys have questions about the slope field and graphing it, please let me know. But that's really all you're doing. You're plugging in the x, plugging in the y, and seeing what the slope comes out as, and trying to graph a little line approximately that point. So there's our slopes. And that's all they're looking for in this one, right? Just sketch the slope field, at the 9 points. They put the 9 points, I drew my slope of my 9 points, and I'm going to move on with the question. So we have find the particular solution at f of 2 equals 0. So this is again where we're going to have to show the separation of variables. So let me go ahead and copy down dy dx as y minus 1. All right, now I have to do the separation of variables. So this would be 1 over y minus 1. But that's not what I wrote. dy equals 1 over x squared dx. That is your separation of variables that you can then do the integration for. So over on the left-hand side, this will be natural log of y minus 1 plus some value of c, right? And then this would be, what, negative 1 over x plus c. Okay, so now I can combine those c's because those are two different c's, so I might as well just put it as this. And that's how I'm used to doing this anyways. So I'm going to start doing that in the next problem too when we start finding our solution there. Okay, so the next part, can be a little bit tricky because you need to remember your rules of rewriting these things, because this is e to the negative 1 over x plus c equals the absolute value of y minus 1. So now the absolute value, that can be plus or minus in there. So the way that I'm going to break this up is I'm going to say, well, let me rewrite this first so that it hopefully makes sense to you guys. Is I'm going to kind of look at it like that. And what I'm going to do is I'm going to say, why don't you let me write, let k be plus or minus e to the c. So the reason I'm writing that plus or minus is because the absolute value there. That means y plus 1 could be plus or minus e to the c, e to the negative 1 over x. And that e to the c is just some constant. You can solve for this constant really any time. I think Mr. Osborne does it up here sometimes, just to make sure that you get that value of c. So it's really whatever you prefer. I don't usually do it until later on in the problem when I kind of have c where I want it to be, so I don't have to do a bunch of math with the number. But it's really whatever. It's anyway, just be careful as you go through the problem anyways. So this plus or minus e to the c, this is really now just some constant of multiplication, which would be k. And now I'm going to use my particular solution, which would be f of 2 equals 0. So when y is 0, x is 2. Right, so k would be 1 over e to the negative 1/2, which would just be e to the 1/2. What did I mess up? Oh, I copied my thing wrong. I'm sorry. Minus 1, minus 1, minus 1, and negative. So negative. I'm sorry. My bad. I just copied it wrong. Okay. So k is e to the negative 1/2. So that means my function y minus 1 equals negative e to the 1/2 e to the negative 1 over x. So the way I could rewrite this is y equals negative e to the 1/2 minus 1 over x plus 1. That is how I would write my particular solution. So, and again, depending on, you don't have to, you can leave all of this separate. You don't have to combine it like I did. They should still accept that. Okay. For the particular solution, find the limit as f of x approaches infinity. So the limit, this is part C here. So the limit as x approaches infinity of my function, which was negative e to the 1/2 minus 1 over x plus 1, right, the limit of all of that, which if I put in, essentially I'm putting in infinity right there. So if I put in an infinity right there, this is 0. So all this comes out to be is 1 minus e to the 1/2. Cool. And that's really all they're going to be looking for on there. So let's take a look. Let's see what solution they gave us and how they want us to kind of write it. I believe it's this one. So let's see, again, they gave us a point for the zero slopes, and they gave us a point for the other slopes. Moving on, separation of variables, the antiderivatives were worth 2 points. Constant of integration is just that plus c. Uses the initial condition. So notice they did it exactly how I did it too. As far as doing the e to the c and solving for c later on in order to rewrite this. They rewrote it a little bit differently than I did, but it was still pretty close. 0 out of 6 if no separation of variables, 3 out of 6 if no constant of integration. So if you didn't include that plus c, you're max getting 3 points. And this last one, they just gave 1 point for the limit, right? I had 1 minus e to the 1/2. E to the 1/2 is the square root of e, so we are good there. Okay, moving on. So again, take your time, go ahead and pause the video, write all your slope fields on there. Notice it's just asking you to sketch the slope field at the given 9 points. We can see 9 points, so go ahead and graph your slopes and see what you come up with. Here's your curves, or your slope field rather, all your slopes, so take a look at those. Again, you can look up the solution online. I'll post the solutions as well. There they are. All right, so part B, find the second derivative in terms of x and y, and then describe the region in which all solutions are concave up. So, to find d squared y dx squared, that will be the derivative of my function. So I need to do the derivative of that, 1/2 x plus y minus 1, which would be 1/2 plus y prime, minus 1 would be nothing, right? And y prime, since I need to do it in terms of y and x, so that would be 1/2 plus 1/2 x plus y minus 1. Right, and I can combine those to make this 1/2 x plus y minus 1. Minus 1/2. All right, so now that's the first part, right? There's my second derivative. So d squared y dx squared. So now to describe the region in which it is all concave up, the second derivative needs to be greater than 0. So that means all of this stuff needs to be greater than 0. We can solve this as a line too, which is how I believe they wrote their answer. So they wrote y must be greater than negative 1/2 x plus 1/2. Either way, that should be the region where we are all concave up, and that should be enough for your answer. I believe they have it a little bit different, but that's really all we need to state in order to give a correct solution. Okay, part C here. Let's see. Y is the particular solution to the differential equation with the initial condition f of 0 equals 1. Does f have a relative minimum, relative max, or neither at x equals 0? So it's not really asking us to find the particular solution here. Right? It's not saying we need to find the particular solution. So what we could do for this to be a relative min, relative max, I want to check first that my derivative at the point 0, 1, I want to make sure that that's 0, right? So be a maximum or be a minimum, the first derivative has to be equal to 0 here. So if I put in 0, 1, that's 1/2 x plus y minus 1. So 1/2 0 plus 1 minus 1. So it is indeed 0. So I do have a minimum or a maximum there. And the next thing that I can do is see what's going on with the second derivative, right? This is the second derivative test. This is where it comes into handy. Because if the second derivative, right, if y double prime is positive, I have something like that, so I'd have a minimum. if y double prime is negative, then I have a concave down, so that would be a maximum. So using this basic information, I can state my answer based on how my second derivative comes out. So let's see. So it's 1/2 x, so 1/2 times 0 plus 1 minus 1/2, which would be positive 1/2. So I could say, since d squared y over dx squared is greater than 0, and dy dx is equal to 0 at the point 0, 1, 0, 1 is a, so let's think about this again, right? I have a concave up part there. I have a point there that is a first derivative is 0. So this is a relative minimum. Yep, that should be enough to answer their question. It may not be like the complete, perfect, ideal answer, but that is the logic that gets you to that answer. So my guess is we're still on base there. All right, this last one is a little bit weird. Let's take a look. So it says find the values of constants m and b for which y equals mx plus b is a solution to the differential equation. So this is what I'm thinking about. And the solution, in order for this to be a solution, the derivative must be equal to n. So in order for that to be true, then I can say if y is mx plus b, so here is my y, and the derivative is m, so the derivative is m, I can rewrite this as m equals 1/2 x, right? 1/2 x plus mx plus b minus 1. Right, so that gets me to that portion. So now, this is where it gets a little bit weird, a little bit out there. We don't see this question show up very often. But if I combine like terms, then m equals 1/2 plus mx plus b minus 1. So now, since I do not have an x on the left-hand side of the equation, so this is where I'm really just comparing sides of the equation, right? This is 0x plus m. What I can do is I can kind of write a system of equations. This is kind of going backwards with systems of equations. So I have 0x's here, and I have 1/2 plus m there. So that would mean if I'm comparing these two sides, that 1/2 plus m equals 0. The other part that I can compare here is that I have m, and that would be my constant, which is what is left, would be b minus 1. So m equals b minus 1. If I solve this left one, m is negative 1/2, and then I can use that here to help me find b, which means b would be positive 1/2. That is really all that they are looking for. Again, it's kind of weird, kind of out there, and how you have to look at it. I don't see this show up very often. I think there's one other example of this in the packet that we gave you, maybe two. I see one on question 9. Yeah, but that's kind of out there and how you have to look at it. But I did want to talk to you about all of those concepts. That's really all you need to be successful moving forward. I don't think there's anything else that's too terribly off base with that. It's just different functions. Approximation one. Yeah, they're all pretty similar. Okay. All right, so that's all I'm going to go over right now. As you guys go through this, though, please check your answers. And let's check the grading on this one, too. We've been doing that all along, so let's check the grading on this one. So let's see. We had slope field correct. They gave 2 points just for the signs of the at each point and relative steepness. So again, they're not checking. They're not going to get a calculator or anything. They're not going to check the exact steepness of everything, but kind of just about this is more steep than this, so on and so forth. Okay. Solutions will be above the line this. That's exactly what we said too. Y is greater than this line. So the derivative they said is 0, which you need to state. The second derivative is greater than 0, therefore it has a minimum at 0, 1. So we had all of it, right? We had the answer that it was a relative minimum. Make sure you call it a relative. And the justification is this entire piece up here, all of that up top. That is your justification. If you're missing a part of that, you don't have a justification. Okay, value of M, value of B. So they didn't necessarily need to see all of this work per se, but if you just make guesses at it, I don't know that they're going to give you credit for it. I certainly wouldn't if you just make guesses at it. So they did the same sort of idea where they kind of look at that as two different parts. So 0 equals m plus 1/2 and m is b minus 1. And then they solve for both of them. All right, other than that, that's really all I got for you guys today and tomorrow. You will have your test on Monday. Can't even remember what the calendar is anymore. But, yep, that's all I got. If you guys have any questions, though, please let me know. We'll talk to y'all soon. Bye.